Today to our presentation on open channel sensor diagnostics. I'm accompanied by Darrell Kuta, another business development manager for flow meter products from Teledyne ISCO. A lot of you have talked to Darrell over the years and perhaps me as well. So we're very excited about this today. Diagnostics are an incredible way of telling you a lot of information. So what we're going to be talking about, the agenda, diagnostics. So what exactly does that mean and why do we need those? So pretty much everything you have today, whether it's a refrigerator or a stove, it will have some kind of diagnostic capabilities, and we're in that same area as well. So why do we need diagnostics and what do they mean to us? Darrell and I have spent a lot of time going through the analysis of data as well as the diagnostics and how to support some of that stuff. So we can use these both during installation to determine that the meter is indeed functioning like it's supposed to, which is a very, very important feature of that. Also, we can alarm in the event of a meter malfunction. So if something happens to my meter, and do I need to go and service it or do anything? So the meter now, being more smart, can tell you when you need to do something. And this, again, is an early detection of maybe equipment problems out there. How we use these diagnostic to quality control our data. So when again, we look at a lot of data, a lot of people out there using these meters for billing, hydraulic model calibrations and all that thing. All those kind of things. So when they look at this data, they want to know it's right or not. And so this diagnostic information can help determine if the meter is working correctly or not. The goal, what is our ultimate goal? It is confidence in the data. So we're all out there installing flow meters because we need data and we need to know that that data is correct. So the diagnostics are a very, very important tool for this. Again, you look at a nice graph like this, how reliable is this data? We have a nice pretty line going up and down, and we have a good table of data on the right. So that all looks great, but how do we know it's right? And so we're going to be talking about that today. So some of you that have been around for a while might look at some of the traditional flow meters or flow monitors. The one on the left is a traditional flow meter. And the way that thing worked was it had, the sensor technology, built-in printer, keypad display, so you could actually visually see what's going on, but there were very little diagnostic capabilities available. It gave you a number and you either went with that number or you didn't. The one on the right is what we call flow logger, and that style was designed to wake up, take a snapshot, go back to sleep. So those are used in applications where you want long power, long battery life, and you don't have a lot of battery capability. So those are kind of the differences between some of the traditional flow meters and flow monitors that you might have seen in the past. All of this diagnostic information, one thing that we do at Teledyne is we are pretty big into technology, obviously. The diagnostics are a big part of this. The flow measurement lab at ISCO, this is in Nebraska. If you ever come out here, we welcome you to visit. But you can see a lot of things on here as far as we use it for design work. We use it for equipment enhancement. We look at diagnostic information. Really, really been a huge benefit, I think, for us in developing product as we go forward with flow. Okay, so we're going to talk about 3 specific technologies today. And one will be the ultrasonic level sensor. And what this does is this is like pretty much what you've seen around for years now, which is a non-contact level measurement technology. And Darrell's going to talk about how it works and things to look for and areas where you may or may not want to use that technology. But those are, again, very popular in flume applications for open channel flow. We're also going to be talking about continuous wave Doppler. And these are sensors typically mounted on a ring in a pipe. They do not require a flume or a primary device. And they will measure the level and the velocity and calculate the flow. These are also very popular for I&I inflow and infiltration studies. There are thousands of 2150 area velocity flow modules out there, and this is part of that technology. And so we've learned a lot going through the years and want to share that with you. laser velocity Doppler. This is going to be the final one we're going to talk about today. And the laser is an incredible technology. We came out with this technology in 2013 and have learned a lot going along the road as well. So we want to share what we've learned, and so those of you that have these different technologies are better able to understand maybe what's going on if you have any issues, and diagnose or at least determine proper operation of the equipment. So with that, I'm going to go ahead and let Darrell get started.
Thanks, Rick. Let's dive into the ultrasonic level sensor. First, we'll talk about how it operates. The ultrasonic sensor transmits a sound wave. It reflects off the surface and detects an echo. And then the level is calculated as a function of time between the transmit and received signal. So depending on how long it takes to get the signal back will determine the distance, which could then be calculated into a level. Now, all ultrasonic sensors have a deadband. And what the deadband is for is the transducer needs a certain amount of time to transmit and then turn around and receive that signal. And what's important about this is that you want to record what the distance is from the sensor to the water surface, and then when you see that the distance is getting close to that deadband, that's going to be a good indication that if it encroaches that deadband, you could actually lose the echo, and then it'll cause an error in your level reading. So the deadband is important. A lot of sensors have a 1-foot deadband, and others may have a smaller or larger one depending on which transducer you have. Now, some things about the ultrasonic diagnostics. We need to calculate level, and then a couple things we need to look at is the distance. So depending on the transducer you have, sometimes you have to enter in what the distance is from the bottom of the transducer to the bottom of the channel to get your overall distance. And then the transducer will then look at and record the distance from the transducer to the water surface. And then we can take that overall distance, subtract the distance to the water, and that will give us our head height or the level reading. Now what that looks like is this graph here. We're showing our level, the normal diurnal pattern going up and down throughout the day. And you'll notice the graph in green is the ultrasonic signal strength. Now, ideally, you want that signal strength to be in the 90% range, indicating you're getting a great return signal as we are on this graph. But look closely, and what you'll notice is that as the level increases, the ultrasonic signal strength starts to drop or decrease a little bit, indicating that it's picking up a little bit more surface turbulence every time the water level increases. Now, if we jump all the way over to Monday the 13th, you notice that our water level increases, almost doubles, and then the ultrasonic signal drops down to about 50%. Now, one thing I noticed with this is that we didn't lose signal at all. It just indicates that, because there were no dropouts in the data, but what we see is that as the level increased, the ultrasonic signal dropped, indicating that during that event, we did have a lot more turbulence than normal. And then after that event passed, it went back to our normal reading. And so the takeaway from this is that you want to just look at the trends to see what happens during these events. And so before it was at 95%, and then after the event, it went back to 95%. It tells me that there's no need to go back and clean the site out because everything has gone back to normal. Now let's take a closer look at the ultrasonic diagnostics. So a couple things, that signal strength is determined by the gain. And the gain on this has a range of 0 to 255. And this one was had a gain of 33, indicating that it, think of the gain as like a volume. It had to turn up the volume to 13% to get a good return signal. And then with that gain, it will determine the quality. The quality indicates how well the sensor locks into that reading. In this one, we're showing that we have a 82% quality. And looking at this graph, so we have the higher bell curve. That was the distance to the surface of the water. However, around at the 20-inch, mark, we're seeing a couple of little bumps in front of there. And so that's what reduced that quality, because it was picking up a little bit of noise when it took this diagnostic reading. But overall, it's looking really good because the gain is low. It doesn't have to try very hard to get a good signal. And then we have a quality of 82%. You want to see your quality at 80% or higher. 90% is what you're ideally looking for. But 82 is still a great reading. Other things you may want to look at is the temperature reading. So looking at that diagnostic report on the right, the third line down, it shows my temperature of 9.1 degrees Celsius. Why the temperature is important is it uses temperature to calculate the speed of sound. And so if you had the sensor out in direct sunlight without a sunshade over the top of it, you may find that your temperature is going to be a little bit higher, which would then incorrectly calculate the speed of sound, which could then result in slight changes in your level. So you always want to make sure that you have a sunshade over your sensor in outdoor applications. And you can also use this for troubleshooting, because if that temperature is unbelievable, it's showing it's like 100 degrees Celsius, we know that isn't possible. And so that would give you an idea that you have a bad ultrasonic pressure or ultrasonic sensor, which then it would be time to investigate or replace it. Now, what we're looking at here is that this graph, we're picking up some false echoes. So you can see the level is averaging about 3 inches, but then occasionally it's dropping down to minus 30 inches. And what that is that we can correct this by using an option to set the blanking distance. So we can set the minimum and maximum blanking so that it only looks for level between, in this case, like 0 inches and 10 inches, and ignores the negative readings. So what that looks like in the ultrasonic diagnostics in the background is that we're picking up some random negative level readings, as indicated by the double bounce shown on the graph. And it's so what's going on here is it's picking up the second echo. So the distance should have been around the 25 inches, but if the second bounce happened to be higher, then it would pick up the second echo, which would then indicate that it was a further distance away from the sensor, which would then result in a negative level reading shown on that previous graph. So how can we correct that? So what we can do here is we can adjust the minimum and maximum blanking distance. By default, it's set to 1 foot and 10 feet or 120 inches. And so we can narrow that blanking distance to 1 foot to 35 inches. So now it's looking at this range in between there, and it will ignore everything outside of that minimum and maximum blanking. So that way, that will eliminate any of the negative spikes we saw on the previous screen. Now let's move on to area velocity flow measurement. Q equals area times velocity, where Q is flow rate, A is equal to area, and area is calculated by the level measurement, which could be either be a pressure transducer or the ultrasonic sensor. The V is velocity, which is calculated by the Doppler shift, which could be either an in-pipe contact sensor or a non-contact sensor to read the velocity. So first I'm going to talk about the contact in-pipe area velocity sensor. And how that works, we're going to calculate flow rate. And we're going to use the pressure transducer to calculate the depth of water. And the depth is going to be used to calculate the wetted cross-sectional area. The velocity, it transmits a Doppler signal into the flow stream, reflects off the particles and air bubbles in the water to read the frequency shift to then give us the velocity, which will determine the velocity of the water and the direction of the water, the velocity. Other diagnostics that we can use with the velocity readings are the signal strength. and it has a range of 0 to 100%, and this determines the amount of return signal. So it transmits the signal, determines how much gain is needed to get a good return signal back. Which then brings us to the other parameter, which is the spectrum strength. It's also on a scale of 0 to 100, but I feel this is the more important of the diagnostics, because we could have the signal strength transmitting at 100% or the gains turned all the way up, but we need to make sure that we're seeing at least 20% of that return signal or higher. And in both these cases, in wastewater, you're going to see the signal and spectrum strength is usually in the range of 40 to 60%. So we transmit the signal, and then the spectrum tells us how much of that return signal that we receive back. Now, the other thing we can look at is the spectrum ratio. The ratio is going to tell us the direction of the water. Now, in most cases, it's going to be a 100%. It sees all the water coming directly at that sensor. But if there's rocks or debris in front of that sensor creating some swirling, you're going to see that ratio is going to start to decrease. So, and what you want to look at is the trends. If it starts at 100% and then it starts going to 75, 50, all the way down to 0, well, we know that there's debris in front of that sensor creating that swirling. And so as you see that signals, the ratio start to reduce, that's a good indication that you need to go out to the site and do some maintenance and clean out the channel. Now, when I look at the signal and spectrum and ratio, as shown in this graph, is I like to look at the trend over time, and we want the consistency. So the signal strength here is averaging around 40%, the spectrum's around 55%, and so I'm not so concerned about what the actual number is, but more the trend. So depending on how clear the water is going to determine the signal and spectrum. So what I'm looking for is that over time, I'm remaining consistent with these readings. If I would see that the signal and spectrum would start to degrade or drop, that would be my indication. That's when I need to go out and inspect the site and possibly clean off debris.
I should say the area velocity stuff, again, a lot of excellent diagnostic information, even more than we went into. We have a nice paper called the 2100 series Whitepaper, and that's free of charge. We'd be happy to provide that to anybody that would like that. That goes into some pretty serious detail on what that sensor does, even more so than what Darrell went through. But great job, Darrell. Thank you. And so let's go ahead. Let's talk about where we're going with different technologies. The goal with us and any of your salespeople should be providing the right product for the application. So let's talk about the latest, greatest, which is laser technology. So how does this thing work? Well, there's an ultrasonic sensor that's in the back of the laser itself, transmits, like Darrell said, the sound wave, reflects off the housing, knows where the water is. And the key with this technology is how it reads the velocity. What it's doing is it's actually focusing the laser below the surface of the water. So it knows the level, knows where the water is, knows where it needs to focus in order to get a return signal. So let's talk about the operation of the ultrasonic sensor in the back. Again, very similar to what Darrell was talking about. It is angled though, and the reason that sensor is angled in this design is to prevent moisture from accumulating on the sensor face. It has a deflector plate. Well, was that designed into it? Well, to eliminate or minimize the effects of the deadband that Darrell talked about. So that means the water will go all the way up to the bottom of the laser before it will not read levels. So that 12-inch deadband is now accounted for in the sensor design itself. So virtually zero deadband ultrasonic on this design. It can be 10 feet away from the water. So it can be, again, a long ways away from the water. See these a lot in stormwater applications, CSOs, big pipes and things like that, where when you do have rain, the world's coming to an end kind of thing, and it can just tear the sensor out. So you want something that's not in the flow, and this technology works well for that. So focal operation. A laser pointer is going to have a constant focal point. So that's why you see a laser beam on a pointer shine forever. What the difference is between the laser technology is the way it reads. What it's doing is changing where it focuses the laser itself. So it knows where the water is, it knows where it wants to get a reading, it will focus that laser below the surface of the water. It's like any other Doppler device. It knows the frequency transmitted, it knows return frequency shift, and that's how we calculate the Doppler velocity on this. Give you a little better idea, front view, side view. When you look at the unit, again, it's taking a distance measurement to know where the water is. If you stuck your hand under a laser, you'll see the dot about the size of a quarter. Where it's focusing is really what you want, and that's called the point of convergence or converging section. We take 5,000 velocity readings, and it does that all in about 2 seconds. So to give you kind of a comparison of technology, a standard area velocity takes about 500 readings. This takes 5,000. So it's doing a lot in a very, very short amount of time. Okay, so what are we looking at? The velocity diagnostic. This is one of the most important features of this technology that I like. And when somebody's setting a unit up or post-processing data, or I'm having a problem with something, we will always almost insist that we get this diagnostic information. This does a couple things. One, it's going to tell us what's called the X angle and the Y angle, which are the pitch and roll of the sensor. So every degree off of 45 on Y is roughly a % error in velocity. The laser sensor itself actually has a built-in accelerometer. It knows the position. So that's how it calculates that. It will correct mathematically for any errors potentially in install or whatever. So when the field crews are in there installing, they know the X angle is 0 plus or minus 3. They're right on that. The Y is 45 plus or minus 3, and they are right on that as well. But really the magic that you're looking for is this signal down here. Megahertz is the frequency or the speed of the water. Faster to the right, slower to the left. The more of the 5,000 scan that agree on the return signal, the bigger this signal looks right here. As a general rule, on the FFT amplitude, anything above 500, we would consider to be a good reading. So this is telling me I have a really, really good signal return coming back. So let's zoom in a little bit more. Here's another site. This is what it's all about, the signal versus the noise. So this is signal to noise ratio. The noise floor is on the bottom. We want very low noise. We made a lot of improvements on the laser technology so that we eliminate that noise floor, minimize that noise floor. What that really means is that the laser can read extremely slow velocity. As that water slows down, that signal that you see there will shift to the left. So 0 is 0. We can read down to, again, roughly, well, spec is 0.5, but a lot of times that laser will read down even to 0.2 foot per second. This is really a measurement of the quality of the velocity reading that you're getting. So when you install, when you go out, troubleshoot a site, whatever you do, you want to download one of these. It's recording, again, in the memory itself. This is known as a reading called, we call Doppler power, and this needs to be greater than 1,000 in order to consider it a good reading. So a lot of diagnostics. This is similar to a 2100 series where the velocity spectrum, that's what we're looking at right here. So the more of the spectrum that we like, the bigger the signal is. Same thing with the 2100 series area velocity. Okay, what does this really tell me? It tells me that the velocity signal looks excellent. Why? What makes up that signal? It's got to have a couple things. One, it's got to have reflectors in the water. Most of these are used in wastewater, so there's typically plenty of stuff to reflect off of, but there are a lot of times that you may have very clean water. Well, would this thing work in clean water? It really depends on how much entrained air is in the water. What do we have in that water that will reflect that laser beam back? So this tells me, again, we'll see these in UV disinfection channels. where your water is typically very, very clean. So, but it will tell you that. It'll tell you that you have plenty of something in the water to reflect off of. The other thing it tells you, it really are the hydraulic conditions. If I had poor hydraulics, similar to what Darrell was talking about in the ultrasonic level signal, you'll see a drop in ultrasonic level signal. You'll also see a drop in the Doppler power reading typically, because not all that 5,000 reading scan are agreeing. So this tells me I have stuff in the water and my hydraulics are good, but it will also tell you if they're not good. Also, again, going along that line, velocity flow profile is very consistent. So a lot of information you can gain from one snapshot of that. The laser can read extremely low velocity, and that's because that signal to noise ratio is so much more so good, I guess. Here is a example of a graph from a site. At this point that I've selected, the level is about 4.7 inches. The velocity, although, is 0.6 feet per second, so it's slow. But the Doppler power number, which is really what I'm looking for, right at the parentheses is where my line is. That's 20,000 Doppler power. So that means I have really good hydraulics, plenty of signal return coming back. Bottom line, as Darrell mentioned earlier, on consistency, this is very consistent. No reason to touch it, clean it, do anything with it, leave it alone. So again, indicating a very good signal. And when you download this remotely, you know with confidence that you're doing what you need to be doing. Okay, I'm going to talk a little bit about the ultrasonic, although Darrell did a great job covering that. But it uses the same sensor as the 310 that he talked about for flume applications or open channel, basic open channel applications. It's important, obviously, to make sure the sensor is level, but it really is an excellent tool to determine the turbulence in the flow. So I have a lot of people that will ask me or look at data and they don't understand it. When I look at that ultrasonic signal, that's one more tool that I'm able to use to really get eyes on the flow. It's almost like I'm watching that flow when this event happens. Really good example right here. This is a CSO line, and you'll notice my velocity or the level ultrasonic. Normally it's dry pipe and you're in the 85% range. Every time they have an overflow condition, you can notice how the level obviously goes up and the ultrasonic signal drops. This is a clear indicator that I have turbulence, actually quite severe turbulence in that channel. So you look at the date on the 14th on that Saturday, that signal ultrasonic went down to almost 20%. That level went up to 50. So the water is getting closer to the ultrasonic, which theoretically would make that signal stronger, not weaker. This tells me it is moving through there and it is very, very turbulent and difficult to get a good surface lock. So again, one more very useful piece of information to determine what's going on at that site. Okay, so I'm going to go ahead and wrap it up here. Diagnostics should be, if they're not, available on most new flow meters that you'll find in the market. And I would highly recommend buying something that has that capability, because the diagnostics are going to tell you way, way more information than just the data alone. We will get graphs that people will send us something from a SCADA system. That means nothing to us. Yep, this did this, it flatlined. We can't tell you anything from that data. We really need this diagnostic information. So whether it's product support or application guys or whatever, we need to know what that meter saw, much more than just the pretty graph alone. Again, invaluable to be used during startup, because you'll know exactly, we will be able to assist you and make sure that that thing is working when you fire this up. We have seen laser applications where we had no idea if it was going to work or not, to be honest, until they installed it. Once we installed it, we can tell, yep, you're working, or no, there's nothing to reflect off of, or whatever, but we can tell you exactly what's going on. So startup is really, really crucial with diagnostic. Troubleshooting, as much as we hate to see anything not work, there are times in every piece of equipment out there where you're going to have problems. And this diagnostic information is extremely important for us to be able to help determine the problems. As corny as it sounds, to me, it's like an MRI, CT scan, X-ray. It is actually telling me what is making up that digital number that I look. So when I look at a number that says I have 8,000 Doppler power, what does that really mean? This, again, diagnostic will tell me exactly what that thing is seeing. Also, again, can be remotely available via modem, and you can call it anytime. If you have an alarm that says, hey, something's going on at the site, 2100, it could be low signal strength. You can call it and go, oh, wow, it must be covered. In the case of a laser, we could see something there and say, oh, it looks like you have, the mount shifted. The sensor itself is off track, whatever. So a lot of things can be available, again, remotely for diagnosing and alarming. And really, it tells you if you need to do anything. Bottom line, in this day and age, nobody wants to go in any manhole if they can all avoid it. The diagnostics will tell you if you need to go in or not. All of the technologies these days should be smart. And if you find smart technology, that's going to improve the performance of the meter. It's going to allow you to mix and match, add different technologies that better fit your application. And again, you want to make sure that the meter that you select has those capabilities, because these are very important, again, going forward with different types of technologies. All right, well, we're going to go ahead and open this up for some questions right now. If you do have questions, feel free to ask them now or email to both Darrell or myself. And the email address is above there, so feel free to do that. I had a couple good questions here I wanted to throw out here. One of them was I used to store signal and spectrum strength on my 2150, but I thought that I used more power, so I turned those off. Is that the right thing to do, yes or no? And the answer to that, that's a good question, because I do get that asked quite a bit. It does those diagnostics every time it takes a reading. So technically, no, it would have no effect on battery life. It would take a little more data storage. So when you download a file, it's going to have more data in it. But no, I would always encourage, at a minimum with the 2150, I would store the signal strength and spectrum strength. Spectrum ratio, what's good about that is, as Darrell mentioned, it will read typically 100%, but we will see sometimes during storm events where that spectrum ratio will drop. That to me is an indicator of severe swirling in the water and things like that that could cause those kind of conditions. So very useful though when you're looking at that information or that data. You can also turn those on as a secondary data rate. So you could turn them off and say when my signal or my water level gets to 2 inches, I know I have an event. Now I want to turn my velocity signal spectrum ratio on. And you could have that go as frequent as 15 seconds. So a lot of capabilities and flexibility there as well. I have another question here. How far does an area velocity sensor penetrate? That is a really good question. Again, we get that quite a bit as well. That sensor will see anywhere from 2 to about 4 feet into the water, roughly. And we will have people that will, quote, scrub sensors. And so what they're doing is they are going out there, they said, yeah, I scrubbed the sensor and it still doesn't read. When you install an area velocity sensor, probably the first thing you're going to see is that is as good as it's going to get for that site. So whatever that signal is and spectrum while you're installing is as good as it gets. If that number drops, then you know you have some silting or something covering it. But we had a case where a customer had a sensor they're having issues with, and what they found was there was a piece of concrete about 4 or 5 feet in front of it, and it was causing some severe swirling of the hydraulics there. So really had nothing to do with what was on the sensor. It was what it was seeing from that. So good question though.
So Rick, we had another question came in. Somebody was asking how they can request the 2100 series white paper. So if you need access to that, please just email Rick or myself, and Sharon is going to send out a email after the presentation. You could reply to that asking for the white paper. We'd be happy to send that to you.
Yeah, that's a really good document. Had a lot of input from a lot of customers out there, and is a real good cheat guide, if you will, for lack of a better word, that really helps you kind of determine, am I getting good data or am I not? So that's one of the, the things behind all this is, how do I know my data is good or not? Okay, so here's a good question. I have I want to use a laser, and laser has multi-point, but what happens when my flow goes down? And I get this question quite often as well. So if I have the laser set, we can do 15 velocity points. When the water level goes down, some of those points might be hitting the outer walls of the pipe and not even hitting the water. So what will happen in the case of the laser is it will throw those readings out. So if it doesn't get enough of a return spectrum like you're seeing there, it's going to go ahead and throw those readings out and use what it had. So that's good. You don't have to actually tweak and adjust when things are happening. Okay, here's one. How clean can the water be? Another really good question. I think our spec is 20 parts per million TSS. And it really all depends. Pretty much everything is reflecting off of something in the water, obviously. And a lot of times that's just entrained air. That can be just little particles in that flow. But we will know immediately with any of our technology, if we're not getting a signal strength back on an area velocity sensor, we know we got a problem. The laser, we can look at that diagnostic as well. So we will know immediately if it's going to read that water. But for the most part, we will read tap water, provided it's moving. So you can read some really clean water, but not in every case. So you just have to try it out and see what it does. Let's see. Okay, here's one. Can we store diagnostic information when the system is in error? And the answer to that is, yeah, we can actually store diagnostics when we have a bad reading. So if you don't want to store them all the time, you can just, again, have it when it struggles to get a reading, go ahead and store some diagnostics. So you can do that with the laser, and that's a good tool actually to use. Darrell, you got any?
Yep, we had a question about the how can you access the diagnostic tools on the 2150 that we were talking about for the signal spectrum ratio. So by default, those are not turned on, but while you're connected to the 2150 with FlowLink software, look on the top right corner of the screen. There's a button that says Jump to Measurements. When you click on Jump to Measurements, you'll be able to branch down, and then you're going to see your 2150 sensor, and it's going to show all the available parameters, which would be the signal, spectrum, and ratio. And then you can select each one and just tell it you want it visible, and then how often you want to store that. Another question that came in was, how can I use the diagnostics on an AV sensor using a 750 module on the 6712? Well, the 750 module is it is a different sensor than we're using on the 2150, and it does not have all the same diagnostics available. So it doesn't store that data. However, on the screen of the 6712 sampler, you can go under status, and it'll show you the real-time signal and spectrum strength. Let's see. We have another question about increasing the battery life on a LaserFlow system. What should we look for in diagnostics? Well, with this one, it's more likely a programming issue as opposed to something with the diagnostics. A lot of times what we'll find is that one of the settings, especially if you're on batteries, instead of taking readings every minute or 5 minutes or 15 minutes, inadvertently, one of the settings is set to read continuously, like every 15 seconds. And so, like if you have a surcharge sensor on there, you may have it looking to when to use the secondary data storage or the surcharge sensor every 15 seconds, which is causing the unit to run all the time. So most likely it's a program setting that you need to look at closely.
Yeah, one thing I guess to add to that is we would really like to see the data file from that. So if you do have a site that's doing something strange, we'd like you to just archive it and email it to me or Darrell, and then we can look at that and kind of see what's going on, how everything's programmed, and so on. Batteries are key on all these. The laser does take more power than a 2150, so it will not, if you're a 2150 user, you're going to definitely notice a decrease in battery life. But you want to make sure you have good batteries to begin with. So the 2150 was a lot more forgiving with not really great batteries, but the laser definitely is going to take more. There's some program changes that could be in there as well, like the laser, and I just kind of went through it briefly, but it knows where the water is, focuses the laser, but it has a couple other settings that'll scan. If it can't get a good reading, it'll scan to find it. If one of those readings is turned on, it'll take more power as well. But all that's available in the program file of the meter. One thing I should mention also is when we collect the diagnostic at 2160, when you download the data, it will download that diagnostic. A signature, you have to actually request it. So it's a little bit different, but those are things that we would want. And anytime you turn on a laser, really any meter, I would always download a diagnostic. That way you have a really good start point. You know where it was when everything was working as good as it could.
So Rick, we got another question came in about the 360 LaserFlow sensor. So like on a new install, if the velocity is reading 0 and the Doppler power is 0, what should we look for? And so a couple things with that. Could be could be as simple as the red cap is still in the nose cone of the LaserFlow sensor, so you want to make sure that's removed. The other thing is you want to take a visual inspection to see where the laser is hitting the water. There is a function in the programming to turn the laser on so you can see exactly where it's hitting. If you don't have it aligned properly and you're hitting the side wall, or we have a low water depth, possibly it's not even hitting the water. It's causing the issue.
Yeah, those are good points. So the one main thing that I've learned over the years, if you take that laser and hold it by your side, you'll see it read a level. The level should change, should lock on the ground. And if that laser pointer is focusing, or the laser part is focusing, it's almost about a 90% that thing is working. So then it comes down to potentially splashing on the window, water droplets on the window, or something like that, which can be corrected easily with a quick clean of the window. But yeah, the main thing is when I don't get a reading or can't get a reading, I immediately download a diagnostic. And what that will tell me is I will see if I have any Doppler shift, any bump at all. The ones I showed in the presentation were very obvious. But what you'll see, if you're not getting good readings, you might see a very weak bump, but you don't see a reading in the Doppler power or the velocity. And that's why I grab one of these so I can see, am I even getting a partial reading back? Once I know that, then I know where I'm at. Another thing that can happen is when we have these on high velocity, real steep lines, and the water's only 1 inch to 2 inches deep, the laser could technically be trying to be focusing below the pipe. So there's a setting in there called steep slope, and what that'll do is allow you to kind of change where it's focusing. But then I always, again, grab a diagnostic so I can see, did that make an improvement on that signal? So just a lot of stuff you can get from, again, the diagnostic information, and strongly suggest you download after you start up one or you retrieve it, or you have any data questions, so we can help you better. With that, I think we are about done with questions. Don't see a whole lot more. Would like to thank everyone. I know Darrell and I would for attending today. And you know, this is just one series of many, and there's just a lot of information. Working from home here. Sorry about that. A lot of information though that we can help you with as you're analyzing data. So once again, thank you very much for attending.